Good evening to everyone in South Africa and a good morning to all our US attendees and presenters. We are super excited for this event this evening. Now, as you can all see, it is entitled 21st Century Medicine. It is time to embrace the future. It is brought to you by the Wits Students Bioethics Society, together with the Wits chapter of the South African Medical Students Association. It is an incredibly important topic of which to discuss and something we need to think about as we are going to be the future healthcare professionals to come. We have two very esteemed guests, but before we move on to them, I just want everyone to be aware that we are recording the lecture. You will see a notification up on your screens. That way we can make it available to everyone after the session, and if anyone does miss it, we can make it available in that way via our YouTube channels. Without further ado, I will be handing over to my colleague Kamira Dyer to introduce our speakers.
Okay, good evening, everyone. The first speaker that I would like to introduce is Professor Lisa du Toit. Professor Lisa du Toit is currently an Associate Professor of Pharmaceutical Chemistry and Senior Researcher of the Wits Advanced Drug Delivery Platform Research Unit in the Department of Pharmacy and Pharmacology at the University of Witwatersrand. Prof. du Toit completed her PhD under the advisory capacity of Professor Vanessa Pillay, who is the director of the WADDP, focusing on drug delivery design in the Department of Pharmacy and Pharmacology. Her thesis is entitled A Bioresponsive Polymeric Implant for Site-Specific Prolonged Drug Delivery. She is a National Research Foundation of South Africa Y1 rated scientist. Her research outputs have established her globally as an aspiring leader in nanosystems, specifically applied to ocular drug delivery. In addition to these publications, Prof. du Toit is the first author of 5 book chapters and has co-authored a number of editorials, books, and chapters in books. These outputs are anticipated to be widely read and cited by researchers in pharmaceutical sciences globally. She recently edited a book in her area of expertise entitled Advanced 3D Printed Systems and Nanosystems for Drug Delivery and Tissue Engineering, published by Elsevier in 2020. Prof. du Toit has also garnered commendation at international conferences, presenting at 13 international conferences. As an active senior researcher of the WADDP, Prof. du Toit supervises PhD and master's students and has graduated 13 PhD students and 24 master's students. In her role as supervisor and lecturer, Prof. du Toit mentors a number of students and has been a recipient of the Therapeutic Science Mentoring Excellence Award in both 2012 and 2019. Professor du Toit is an inventor on 9 granted patents and on a number of PCT applications filed internationally. Amongst many awards, Professor du Toit received the TWA
Kamira, I'm so sorry to interrupt, but I think your mic is muted.
Was it muted the whole time?
No, it only muted like a couple seconds back.
Okay, so I'm going to just go on from the top of the slide. So as an active senior researcher of the WADDP, Professor du Toit supervises PhD and master students and has graduated 13 PhD students and 24 master students. In her roles as supervisor and lecturer, Professor du Toit mentors a number of students and has been the recipient of the Therapeutic Science Mentoring Excellence Award in both 2012 and 2019. Professor du Toit is an inventor on 9 granted patents and on a number of PCT applications filed internationally. Amongst many awards, Professor du Toit received the TWAS Young Affiliateship, which is an honor given to only up to 25 developing nation researchers with at least 10 international publications demonstrating potential for high-impact career. Recently, in 2021, she was elected as the Vice President of the South Africa chapter for Controlled Release Society. Welcome, Professor du Toit, and thank you so much for making the time to engage with us this evening.
Thank you so much for having me.
Okay. Our second speaker this evening is Dr. Patrick Soon-Shiong. Dr. Soon-Shiong is a physician, surgeon, scientist, inventor, technologist, and philanthropist who has devoted his career to understanding the fundamental biology driving life-threatening diseases and translating these insights into medical innovations with global impact. He serves as chairman of the Chief Executive Officer of NantWorks, an ecosystem of companies with deep understanding in a wide variety of complex industries, from medical sciences to physics, from data to AI, and from communications to mobility. Dr. Soon-Shiong was born in Port Elizabeth, South Africa, and received his medical degree at the University of the Witwatersrand in 1975. He was the first Chinese intern granted permission to serve his internship at the Johannesburg General Hospital during the period of apartheid. Following a period in the TB clinics in East London, he left to continue his training as a surgeon at the University of California, Los Angeles. Later, he was appointed the role of Assistant Professor of Surgery and Assistant Professor of Medicine at UCLA. Dr. Soon-Shiong led the development of the California Nanosystem Institute and received support from NASA and NIST to develop next-generation biological materials. Over the course of Dr. Soon-Shiong's career, he has pioneered novel therapies for both diabetes and cancer, including the revolutionary drug Abraxane, which received FDA approval for the treatment of metastatic breast cancer, lung cancer, and advanced pancreatic cancer in the US and the EU. He has published more than 100 scientific papers and has been granted more than 400 patents worldwide for groundbreaking advancements spanning a myriad of fields of technology and medicine. As a surgeon, Dr. Soon-Shiong performed the world's first encapsulated human islet transplant and the first engineered islet cell transplant and the first pig-to-man islet cell transplant in patients with diabetes. Thank you so much for being here, Dr. Soon-Shiong. We welcome you to our webinar, and thank you so much for engaging with us this evening, or in the morning on your side.
Well, thank you for having us. Do you want us to start? I'm sorry, I can't hear. I'm not sure whether you're ready for us to start.
Yes, we would love for you to start.
Okay, thank you for having us. And I think what a pleasure it is for me to speak to students. And this brings me back to my day, and I wanted to share this picture of the second year class of 1971. And as you could see, the honor of being taught by Professor Tobias, who's really a hero to mankind, have discovered as you all know, the first modern human. And I think the ability of South Africans to be taught by giants, and I can get the next slide, of medicine, and from just by history, from 1970 to 1976, truly I had the privilege of being mentored by these giants of medicine. Professor du Plessis, as some of you may know, would provide an ethics lecture every Friday. And one was the pioneers, not only in surgery, but discovered against dogma, part of the cause of gastric ulcer. Professor Bothwell, who was a pioneer in iron metabolism in cancer. Professor Tobias, who, as you know, discovered the modern human. Professor Barlow, who with mitral valve prolapse, and the syndrome is named based on his name, the Barlow syndrome. Professor Harry Seftel, infectious diseases, and Professor Myberg, who did the first kidney transplant and liver transplant. It's remarkable. These are the giants that are at WITS, trained many physicians and scientists. And to us today, for me, it's such a pleasure to be able to talk a little bit about what we've done since I left the country. The next slide. In 76, as some of you may know, the Soweto uprising, and I volunteered at Baragwanath. And in 77, I spent time in the TB clinics, which said to me that the way I needed to really come back one day and bring technology, because it was very hard for me managing patients without any resources to know what we're doing for the patient. And one of the things we learned from these giants of medicine is the only thing that just matters is that of the patient. So I took the opportunity to leave the country. Next slide. And I don't expect you to read this slide, but there are now these are the organizations that I founded, are live, and all of you could go into these websites. But there really are three pillars that I was really concerned about and still am concerned about that will affect generations to come. And clearly health and life sciences is my core. But without us understanding climate change and energy and renewables, which is the second column, and I really think the opportunity of AI, and especially this conference, recognizes that in terms of what I call cognition and creating connectivity now with 5G and the new spectrum going to be called WiGig, allowing real sensors happening, and I call this the human signal engine, so that we can capture vital signs, capture genomic sequencing, and know and predict way in advance whether and what you should do on behalf of the patient before disaster strikes. So I'm not going to be able to go through in the 30 minutes that we've been allocated these three columns, but let me focus really on cancer. Next slide, please. And I think very much like my training in South Africa, where because we were willing, very much like Professor Du Plessis and all the other professors, to take on dogma and not accept what is perceived as even today, that cancer is a single clone, and that way to kill cancer is give maximum tolerated dose of a toxic poison called chemotherapy or radiation and hope to kill this cancer clone. Unfortunately, cancer is not a single clone, it's multiple clones. Next slide. And next slide. I think this proves it. There's a targeted therapy. If you look at column A, this patient with this cancer, and the magic of targeted therapy with an oral drug, and within 9 weeks, next slide, the resistant clones appear. So ironically, the whole world of targeted therapy has said there was no magic bullet. And if you look at cancer, the way we treat cancer worldwide, and still to this day, we still have not recognized that because of this clonal disease, and if you look at what we call the standard of care of high chemotherapy, and you treat the cancer, and on the right, what happens was the surviving cell clones survive, because they have an ability to hide from the immune system. Next slide. Not only do they have the ability to hide from the immune system, they have the ability to turn off our killing cells, which is really the CD8 memory killer T cell, the natural killer cell, and suppressor cell called the dendritic cell. So here's a real interplay now of the immune system. And by the way, as we speak about cancer, you'll soon learn our approach to COVID. There's really no difference between the approach to COVID and approach to cancer. As this cancer finds a way to not only hide its surface receptors and suppress the killer cells, it now spreads. Next slide. And it spreads with what I call micrometastasis until it reaches what we call the cancer stem cell. And we, unfortunately, as physicians, said this is now incurable. leading us to the dreaded disease. And cancer for Africa is going to be one of the highest non-communicable diseases, together with infectious diseases. So there really has to be a completely different approach to this consequences of standard of care, which I call tolerogenic cell death. So I spent my career in this country trying to understand these molecules, understand the interplay of these molecules. Next slide. And I've now taken the concept and I've launched this term only because I want people to think about it, called quantum oncotherapeutics. And the meaning of that in my head was that cancer changes. The only thing constant about cancer is the ability to change, mutate, very much like COVID, the ability to adapt, the ability to actually predict based on the treatment you give, how it's going to mutate and metastasize. So it's like a chess game, we have to outthink it. So this concept of immunogenic cell death rather than tolerogenic cell death is a concept that I think will change the paradigm of cancer care. And I've spent maybe 25 years of my career reaching the point of trying to prove this concept, and we call this the NAND cancer vaccine. So let me take you through this as rapidly as I can within 5 minutes, where one of the first steps is how do we block the ability of the cancer cell to evade the immune system. Ironically, COVID and infectious diseases and viruses like COVID have found ways to evade the immune system. And the three main players here are the thing called the Treg cell, the M2 macrophages, and myeloid-derived suppressor cells. These are cells in your body that are important because it prevents autoimmune disease. So this is the balance, the check and balance of against the killer cells. The cancer cell has figured out a way through a thing called TGF-beta to upregulate these suppressor cells. So we have to find a technique not only to suppress the suppressors, but to activate the killers. And next slide. And I'm going to try and take you through that process. So the first step, as I said, is to overcome the suppressors. Actually, the very first step is to actually not perform the standard of care, which is a very, very difficult conversation to have. And as young students, especially in the bioethics organization, where you ask yourself, is it possible, inadvertently, mankind and oncologists and even the NCI that started with toxic mustard gas as chemotherapy over 40, 50 years ago, could be responsible for inducing metastasis? Because with the standard of care, the first thing one does is actually kill the entire killer cell system. So by avoiding the standard of care and giving what we call low-dose metronomic chemotherapy, we were able to overcome the suppressors and using the what I call chemoimmunomodulators to suppress the Treg cells, suppress the M2 macrophage, suppress the myeloid-derived suppressor cells. And now you overcome the suppression effect, but that's not enough. Next slide. We now need to expose the tumor. And by that, I mean we need to expose the expression on the surface of the cancer cell so that our natural killer cell and T cells can recognize it and kill it. And in so doing, we induce the concept of DAMPs and PAMPs. When you have an infection, when you have damage, as you're growing stem cells in your body, there are errors, and these are molecular patterns that your body recognizes and exposes your natural immune system to kill either infected cells or damaged cells. And that was one of the bases of my inventing Abraxane. This protein nanoparticle would enter the tumor microenvironment and expose the tumor cell. But that's not enough. The next slide. We now need to activate what we call the innate system, and that's the natural killer cell. But that's still not enough. We now need to activate the dendritic cell. Next slide. So that we can inform our body about the future, i.e. generate memory T cells. And again, this is why this to me is so important for COVID. In order for us to fight this pandemic, we need T cells that have memory. Next slide. And therefore, in order to do that, we need to not only kill, but remember. So if you look at 1, 2, 3, 4, and 5, you overcome the suppressors, you activate and expose the tumor, you activate your natural killer cells, you inform the body about the dangerous antigen, you generate gamma interferon memory killer T cells, and remember. It looks like a simplistic concept. It's complex orchestration. Next slide. And if you complex orchestrate this as 1, 2, 3, 4, and 5 in a pattern, one would then kill the surviving cell fraction, kill the clones, prevent micrometastasis. And over the since 2016, with the help of the FDA and visionary regulators such as Dr. Pazder and Dr. Peter Marks and Dr. Jeffrey Sloan and Janet Woodcock, enabled us to enter into what I called QUILT trials, number 7. And I call this, next slide, quantum combination, so that we could enter QUILT trials. And what I mean by QUILT, again, is another acronym we created called Quantitative Integrative Lifelong Trial. And if we could prove this concept of immunogenic cell death, we entered into trials for bladder cancer, pancreatic cancer, Merkel cell cancer, triple-negative breast cancer, head and neck cancer, lung cancer, colon cancer. I've now tested this concept in over 500 patients across multiple diseases, all that have failed standard of care, to try and generate what we call durable disease control and complete remission. I'm reticent to say the word cure until we really fully understand how to create long-term cures. So for the rest of my talk, this complex slide of quantum oncotherapeutics, this whole new young class, I can't see you, but I'm sure this is something that's in your future. So let's talk about the efforts from 2008 to 2021, the quest. It's very appropriate today with regard to drug delivery as part of the symposium. In 1991, as part of a NASA program, I was fortunate to be part of the space shuttle program. We put our experiments on the shuttle, and with the grant of NIST, the idea arose that the human body, most important protein in the human body is albumin. It also occurred to me that regardless of tumor type, you lose weight. It also occurred to me that perhaps the common denominator is that the tumor sucks in albumin. If it does that, then could we create a nanoparticle of albumin and trick the tumor to feed on the albumin like a Trojan horse, but add paclitaxel inside the core, and thus became Abraxane. So rather than starve the tumor, around that time, there was Avastin and people saying starve the tumor. And that scared me because starving tumor would allow the tumor then, frankly, to actually spread. And I thought feed the tumor. And in 1991, that was very controversial. Luckily, the drug was approved by 2004 for breast cancer and lung cancer and then pancreatic cancer. Next slide. And indeed, what we showed that what albumin did was fed the tumor and brought the paclitaxel to the tumor microenvironment. So that was step one in this quest, and one would think with the success, that would be the end of the story. And sadly, that was the beginning of the end, because all that did was expose the tumor and was step one of this quantum oncotherapeutics. Step two was to identify how to bring in natural killer cells. Next slide. And this natural killer cell is what you and I have in our body. And part of my trip out of South Africa is I went to Vancouver General Hospital first. And in Vancouver, at the Vancouver Cancer Center, Dr. Hans Klingerman in 1992 identified a patient who had a cancer of natural killer cells, a very, very rare cancer. And he had the foresight to take the tissue and put it into the incubator. And the story goes, the technician put it in incubator, and over the weekend, by Monday when they arrived, the cells had proliferated to such an extent. And these natural killer cells were stem cells, or NK92s. So here was the opportunity to have a stem cell called the natural killer cell that we could then engineer and target. And what you see here, the red is a breast cancer cell and the green are normal cells. And this is under the microscope. And as I play this video, you'll see the cell hunt down the cancer cell and through perforin and granzyme destroy it. And this natural killer cell on the right-hand side, as you'll see, is able to kill. So we have within our body then a natural killer cell that we either have or I could engineer off the shelf. So the next 4 or 5 years were to develop techniques to grow these cells in an unlimited supply, to engineer them with sequences and freeze them so that it could be transported anywhere in the world, including to South Africa, and infuse as an outpatient over 30 minutes, 2 billion cells. And we've now succeeded in cryopreserving these natural killer cells. Next slide. And infusing them as part of a protocol in the United States. Next slide. But more excitingly, scaled to the point that we now have this large scale, trillions and trillions of cells that we can manufacture and cryopreserve. In the lower left corner, you see these tanks of cryopreserved natural killer cells. One of my ambitions is to bring this home, is to bring this to countries like South Africa, like Africa, where clearly diseases that HPV, cervical cancer, head and neck cancer, lung cancer, breast cancer, pancreatic cancer, where the biology of cancer rather than toxic chemotherapies can be administered. Next slide. So does this work? Is it correct that the hypothesis, could we get complete remissions? And as I said, the clinical trials began, and through the vision and support of the FDA, we were able to initiate a trial where in bladder cancer, we gave 2 molecules, just BCG plus an NK cell activator called IL-15. In Merkel cell carcinoma, we gave 3 molecules, our NK cell off the shelf plus a checkpoint inhibitor plus a chemotherapy. When we got to pancreatic cancer and triple negative cancer, we gave 11 molecules. And head and neck, 11 molecules. And all within 3 weeks, all as an outpatient. And this is what has happened. Next slide. In bladder cancer, there was complete remissions. More data will be presented on Friday, so I can't give you that heads up today, but tomorrow at the American Urological Association, the results of our phase 2/3 trial will be presented in these patients who have no other therapy left for them other than to have their bladder removed. And for these patients with the bladder removal, there's 8 to 9% mortality in very elderly, sick patients. Next slide. In Merkel cell carcinoma, a terrible disease, and a patient came to see us, failed everything, and within 3 months had a complete response. And now to September 2021, over 5 years, complete remission. And there's been no treatment since July 2019. Next slide. When it comes to pancreatic cancer, which is something I pursued most of my life, I'm pleased to say we have one patient now over 10 years, and this patient just most recently had a complete remission after having failed all standard of care. Next slide. When it comes to triple negative breast cancer, we've had 3 complete remissions in 3rd line, and some of these patients now over a year. Next slide. And in, next slide, head and neck cancer. One sees again a patient that was told to go to hospice by both UCLA and Cedars-Sinai, came to see us and had a complete response, and this lasted for over a year. So I think, next slide, that this concept of quantum oncotherapeutics in the field of cancer now has an opportunity for me to explore in multiple randomized phase 2/3 trials, and that's what we're doing. So in the time that remains, let me turn my attention to COVID. In 2020, and I'll ask you to go to the YouTube, and I tried to really sound the alarm in March of 2020 and April of 2020, and ran a series in the LA Times called The Science Behind Coronavirus, in which my fear was if we go to the dogma of vaccinology of antibodies, we will be generating what I call typhoid Marys and have the virus mutate against these antibodies. And the wild type variant, which was there then, unfortunately, has now become the beta variant, the lambda variant, the delta variant, the mu variant. It said that we really need a T-cell vaccine, meaning we need both antibodies and T-cells. And I'm pleased to say that working with SAHPRA, we have now initiated what we call the Sasonki Boost trial, in which we're boosting the Johnson & Johnson and the Pfizer vaccine in South Africa, and it's now phase 1, 2, and 3. I hope with Wits, Dr. Shabir Mahdi, to launch the TEMBA trial, and we've already talked to South Africa about a phase 1/2 TEMBA trial. And what's exciting to me about the TEMBA trial would be the first trial, to my knowledge, that will integrate both an RNA and a DNA vaccine and drive T cells as well as antibodies. And I'll show you some data that has not been published. It's not widely published yet. So the next slide is this concept of taking a heterologous RNA, DNA, T-cell vaccine and using a self-amplifying RNA with a nanoparticle lipid carrier. So the world of nanoparticles persists, whether it be in the Abraxane or as a carrier of RNA. The difference here is that the nanolipid carrier allows the RNA to be on the outside, so both the NLC can be manufactured independently of the RNA, and billions of NLCs could be stored. So this investigational agent is called AHI-SC2, in which we will then institute that as a prime. and then followed by a boost of a DNA vaccine, which is our second generation adenovirus. Next slide. I'm pleased to share with you some of the data. And in my career, I have never seen T cells, which is the purple, anti-SCD8 positive T cells on the top left corner at a level of 10% for the wild type. And then the beta variant, which is the variant which was first discovered by Tulio de Oliveira in South Africa. 10% against a beta variant against S, and then on the N, T cells to N. So this would be the first vaccine that would give you T cells to both S and N at this kind of level, 5 to 10% killer T cells. The next slide. So that's the prelude of what we call not being fearful of going against dogma. I'm grateful for being mentored by, I consider these giants, not of medicine just in South Africa, but of the world. And look forward to answering any questions. But I'm grateful for the fact that I was a member of NUSAS at WITS, and so pleased that my first lecture back to South Africa is to the students. I'm happy to take any questions.
Thank you so much for such an amazing presentation, Dr. Patrick. I'm sure we can all agree that it was really amazing to listen to you and gain so much knowledge. I'm Simran, and now I'm just going to ask you some questions that we have. Please let me know when it's fine to begin.
Ready?
Simran, I think we can begin. I just want to check, Dr. Soon Shiong, can you hear Simran as she asked the questions?
I'm afraid not. So.
Can you hear me now?
Yes, I can.
Okay, so can I begin?
Yes.
Okay. So the first question is, do you believe that South African medical schools and teaching hospitals will reach a stage where they are able to train and retain specialist medical personnel within the public sector at a level that mirrors what many international institutions offer to a very limited number of South African students?
Well, I think the opportunity now for the country to actually, and that's hopefully one of my ambitions, is to bring back some of the teachers that have had the opportunity to, having left the country, to come back and train this next generation or cadre of students. I think the opportunity for the medical school, frankly, is to leapfrog the world, because very much like landline or telecommunication has gone to wireless, I think the standards of care have evolved so rapidly. There's advances in science with genomics and understanding, and proteomics and understanding the immune system. We could leapfrog, we could teach a whole new cadre of students in modernized medicine and leapfrog the world. So the answer is absolutely yes, and you should have complete faith. There are brilliant people in South Africa, innovative young minds that I absolutely believe would be able to stand up against the rest of the world in terms of its intellectual power.
Thanks, Dr. Patrick. That sounds really amazing for the future of South Africa. And the second question is, what can student physicians do to keep up to date with advances in medical technology in such a rapidly changing landscape, given that lecture series such as this are few and far between?
Well, the first point is to make them not few and far between. So one of the opportunities is, I'm talking to people like Dr. Michael Crow at Arizona State University to create what we call distance learning. And I'll be working with both WITS and University of Cape Town, University of Stellenbosch, KwaZulu-Natal, University of Port Elizabeth, to figure out a way in which this distance learning could be a regular event, a weekly event, maybe a daily event. So that opportunity really exists. And that boils down to the third column of my effort here of communications and connectivity. And one of the things that I think South Africa is blessed with is fiber connectivity. And that's one of the things we have to sort of bring to the nation for access to information in real time.
Thanks, Dr. Patrick. Hopefully we can see that happen soon because it would really help us all. The next question is, how important do you believe it is for clinical practitioners to develop a deep understanding of computer science related topics?
Well, when you talk about computer science, and when you think about what we do at the genomic sequencing level and what we call the field of bioinformatics, I don't think clinicians need to be bioinformaticians, but we really need to partner. I have a big team of bioinformaticians, amazing computer scientists. So absolutely, the integration, the cross-fertilization of bioinformatics, which then boils down to supercomputing, mobile access of real data, actionable data, is something that we will be bringing. There's a company that I've just developed in the United States called Astra, where we can now monitor EKGs in real time and through artificial intelligence tell whether the patient has a long QT interval or not, and create alerts and alarms. And soon there'll be biosensors where you could monitor somebody remotely for 30 days. All of this requires computational analysis and computer science. So it's going to be very, very important to have that cross-integration.
Thanks, Doctor. And the next question is, in a highly resource-constrained setting such as South Africa, what developments or regulatory changes do you believe should be undertaken to best propel our healthcare system into the future?
Well, that's one of the things why I wanted to ensure we had all the standards that connect. And SAHPRA, as you know, is probably one of the most advanced in the continent of Africa. I've been blessed when I came to this country and ran a company called American Pharmaceutical Partners, where we manufactured 1 million vials a day of 150 FDA-approved products. So we've had sufficient experience now for 20 years of manufacturing and regulatory understanding of how the standards of the FDA and the European Union work. And I'm working very closely with SAHPRA. And my goal is to bring manufacturing capacity to the country, but under the standards of the what we call international standards, ICH guidelines. And if we could do that, the goal would be to manufacture to such a standard that anything manufactured in South Africa could be exported to Europe and to America, because it meets all those kinds of standards that we've now established for ourselves here in this country. So the opportunity to enhance regulatory standards, both in sub-Saharan Africa and then move it across the entire Africa and generate what I call self-sufficiency of that continent, is one of the next chapters of my life in which I'll be devoting, I hope, a successful opportunity to actually create self-sufficiency for the continent.
That sounds really exciting, Doctor. Hopefully we can see that manifest soon. And the next question is, does increasing the use of technology in medicine negatively impact the cost to the patient?
No, I think quite the opposite. I think the use of technology would actually reduce the cost to the patient. I think the concept, for example, of remote patient monitoring, the ability to actually create predictive tools and capture the patient before disaster happens, and actually move from illness to wellness, will actually, at the end, long-term, reduce costs. And boy, by the way, these are tough student questions, so good for you.
Thank you. And why should we use and robots as part of their roboticizing our patients?
Sorry, you just broke up. Say that again.
Why should we use microchips and robots as part of therapy? Are we roboticizing our patients?
No, I think, you know, together with the prosthetic devices, together with some of the elements of robotics, whether it be in the patient, for the patient, or with the patient, is going to advance what you do, including manufacturing, by the way. So the team that's working on robotics should pursue that. And again, it will only contribute to the well-being of the patient.
Thanks, doctor. And for another super long question, do you agree that the ethos and skills of palliative medicine or care should be incorporated into the mainstream of teaching curricula of both the medical and nursing undergraduate and postgraduate students? Also, do you agree that it should be made a failing subject as it is in Hong Kong?
You're asking me whether it should be made a failing subject. I think medicine is an ever-learning subject. I'm still learning. I'm still studying, and I think the opportunity to go from undergrad to postgrad and beyond is really important. I don't know if I can speak to what becomes failing or not failing. It really depends on the your major and your minor. Having said that, if you know, when I went to WITS, I was in high school, and unfortunately, as you know, during the days of apartheid, we went to Chinese high school, and my teaching, the training there was not the best, and I was petrified in my first year of medical school. So I think it all needs to be put into perspective of the opportunity that's given to the students in their undergrad. But so the answer is you need to continue studying, continue learning, and it's a ever-changing evolution as we understand the biology of man.
Thanks, doctor. And to continue that question, do you agree that it combines the art and the science of medicine, which is essential for producing good doctors, as too many use technology for diagnosis, etc., and no longer take essential histories, nor do full examination of patients, which is the art of medicine? And do you agree that not doing this has serious economic implications as a result of the number of expensive tests being done, most of which are unnecessary in order to make a diagnosis, when a history and examination give or hint at the diagnosis in 75% of situations?
What a great question. You know, I think that's one of the value of training in South Africa. I mean, medical school training in South Africa, as you may know, you get allowed to go from high school and do a 7-year training course. And within that phase, history, physical exam is so critical, and you become not a specialist, but a generalist, and understanding first the history and physical. So the answer is absolutely. We trained in both the English and South African method to take the history and physical, and that literally over the telephone, one could make a diagnosis based on taking a very detailed history and physical. So it's a completely important question, and the danger of going too much into the technology world and especially with, for example, even robotic surgery. I fear that, could a surgeon really be able to do a major operation without the assistance of robotics? So to answer that question, absolutely. The value of history and physical is invaluable.
Thanks, Doctor. I'm going to take my history and exams much more seriously than I have been. So, Dr. Patrick, it seems that there is an increasing concentration of talent and in many cases, lower resourced countries typically play an observer role by retrofitting proven innovations once it's available, for a lack of a better world. South Africa and many similar countries seem to be left behind. And my question to you is the following. If you had to start your journey again as a recent medical school graduate today with your level of ambition, what would you consider in terms of geographical location and topics for further education, and why these choices?
Well, I left the country because I wanted to understand technology and where it was, and was fortunate enough to receive appointment at the University of British Columbia in Canada, then moved to UCLA and was involved with NASA and NIST. But I do believe, however, that the technology has now become so widespread. In my time, the internet didn't exist. Distance learning didn't exist. So rather than try and find opportunities elsewhere, I think the real challenge and the real opportunity is to create those opportunities in South Africa, so that the clinical material, meaning 60 million people with diseases that actually you don't see in the Americas, cervical cancer, HPV, TB, schistosomiasis, kwashiorkor even, words that Western countries don't even understand. So it is important, I believe, to actually find innovations at home, develop them in the country of need, and actually provide the help to the community at need, rather than to look outwards. So I hope to encourage people to stay home. The innovation is there, the opportunities is there, and most importantly, the need is there. I'm afraid I'm going to have to take off because I've got another meeting, but if there's one more question, I'm happy to take it. And congratulations on very thoughtful questions.
Thanks, Doctor. We can just do the next question. The question is, do you have a pipeline for ADC drugs for HER2-negative metastatic breast cancer?
Yes, we do. In fact, we are in clinical trials with metastatic breast cancer and metastatic pancreatic cancer and metastatic lung cancer and metastatic bladder cancer soon. So I think the message I'm trying to give is that the cancer itself doesn't regard the anatomy. The biology of the immune system is really cross-functional, regardless of the anatomy. And the treatments that I shared with you that had a complete response had common therapies to activate these natural killer cells and T cells. So the good news is the answer to that is yes. So with that, I have to take off, and I really want to thank you for this opportunity to speak to the students. I love speaking to students, and I love the fact that the students are asking very tough questions, and I encourage you to do that. Never be fearful to ask tough questions.
Thanks, Dr. Patrick. It was all my colleagues. It was an honor having you answer our questions and give such an amazing, insightful presentation. We have learned so much, and we appreciate all you have taught us today. I'm now going to give the platform to my colleague, Previn.
Thank you so much, Simran, for that. And thank you so much, Dr. Sun Xiong, for that very innovative and revolutionary lecture, for which both the Brit Students Bioethics Society as well as SAMHSA are truly indebted to you for. In my culture, we often believe that when you impart education, it's one of the most valuable act one can do, and for that we will ever be so indebted to you. Thank you so much. I would now like to introduce our next speaker, Professor Lisa du Toit, who is a leading NRF wide-rated scientist at the top of her field in pharmaceutical chemistry. She currently serves as an associate professor and the head of pharmaceutical chemistry, as well as a senior researcher at the BITS Advanced Drug Delivery Platform at BITS University in the Department of Pharmacy and Pharmacology. Professor du Toit has also been my supervisor and my inspiration for many years, and I've been so fortunate to garner such a wide array of skills under her leadership. And we've actually co-authored a paper together under her direction, for which I'm so grateful for, and it was about 3D bioprinting for tissue engineering. Without any further ado, I'll hand you over to Professor du Toit. Thanks.
Thank you so much, Previn. And I feel very honored to be invited to this presentation this evening and to follow that amazing and illustrious talk by Dr. Sun Xiong. I'm going to share my presentation. I'm going to switch my video off just so that it is a bit clearer. Good morning to all our colleagues that are listening in the US, and of course, good evening to all of you that are listening currently here in South Africa. I'd like to say thank you so much to Previn for organizing this talk, and thank you so much to Dr. Sun Xiong for that really inspiring lecture. From my side today, I'll be discussing some progressive tissue engineering technologies with a specific focus on what we have been doing in our labs at the BITS Advanced Drug Delivery Platform, which is within the Department of Pharmacy and Pharmacology at BITS University, and how these are so important for furthering 21st century medicine. So first of all, I'm going to highlight what the BITS Advanced Drug Delivery Platform is as a research unit. Founded by the late and great Vanessa Pillay, it is so much more than just a drug delivery platform. We conceptualize, develop, and evaluate patient-centric therapeutics, which ranges from targeted drug delivery, nanomedicine, which I call my baby or my area of interest, biomaterials, which form the basis of most of our technologies, and tissue engineering and regenerative medicine, which go hand in hand and will be the focus of my talk today. But of course, all of these aspects will tie into developing tissue engineering and regenerative medicine technologies, specifically the use of biomaterials and nanomedicine, of course, because we are going down to the nanoscale in developing tissue engineering technologies. Also, near the end of the talk, I'll tie in some other aspects, specifically with a focus on other 21st century treatment approaches. Firstly, let's look at some definitions. So tissue engineering is a very interdisciplinary field applying the principles of engineering and life sciences towards the development of biological substitutes that restore, maintain, or improve tissue function. If we look specifically at tissue engineering, it aims to induce tissue-specific regeneration processes by assembling functional constructs that restore, maintain, or improve damaged tissues or whole organs caused by various factors such as disease, injury, or congenital disabilities, so that you can overcome the well-known drawbacks of organ transplantation, such as donor shortage and need for immunosuppressive therapy. Tissue engineering evolved from the field of biomaterials development, which is the practice of combining scaffold cells and biologically active molecules into functional tissues. Regenerative medicine is a broad field that actually encompasses tissue engineering, but also incorporates research on self-healing, where the body uses its own systems, sometimes with the aid of foreign biological material, to recreate cells and rebuild tissues and organs. As scientists, of course, it is very important to base our work on the underlying mechanisms implicated in tissue repair in the body so that we can replicate this as closely as possible in our design of tissue engineering and regenerative technologies. So we all know that cells are the building blocks of tissues, and tissues are the basic unit of function in the body. Groups of cells generate their support structures, which is the extracellular matrix, which is essentially a scaffold that does more than just support the cells. It's also going to be a relay station for various signaling molecules. So these cells receive messages from various sources that become available from the environment, and each signal can start a chain of responses that determines what happens to the cell. So by understanding how individual cells respond to signals, interact with their environment, and organize into tissues and organisms, researchers have been able to manipulate these processes to mend damaged tissues or even create new ones. So really what you're starting with is building a scaffold from a wide set of possible sources, which for us is essentially polymers and can be any protein to plastic molecule. Once the scaffold are created, cells, which can be with or without a cocktail of growth factors, can be introduced. And if you get the right environment, a tissue develops. In some instances, cells, scaffold, and growth factors are all mixed together at once so that you can allow the tissue to self-assemble. If we look at 3D printing as a tissue engineering approach for creating scaffolds, it was considered a highly futuristic technology, but it's quite commonplace with a layperson even today. It uses basically a layer by layer approach to create a physical version of a 3D digital image. Over the past 15 years, it's expanded into the healthcare industry for creating personalized medicine, and is fast becoming established as an advanced and transformative manufacturing technique for creating a solid 3D object from a digital model on demand at a relatively low cost to create customizable, this is where the personalization comes into play, of course, complex shapes, surfaces, and architectures from diverse materials. Now, if we take this a step further to 3D bioplotting, this is a specialized arm of 3D printing that uses biological materials in computer-aided tissue engineering to create structures for enhanced biomimicry. What the goal is to create an effective combination of cell and bioactive components for restoration and improvement of biological functionality. In our edited book, which we published last year, we examined various 3D printing approaches and nanosystems for tissue engineering, as well as emphasizing the convergence of 3D printing and nanotechnology. I have highlighted that three-dimensional printing is rapidly forging its niche as an advanced and transformative field technology, and it has significant application in pharmaceutical sciences for creating bio-inspired solid 3D devices from a digital model with customizable complex shapes, surfaces, and architectures. The noteworthy applications of 3D printing include the design of personalized 3D printed oral tablets, drug delivery devices, and of course the tissue engineering scaffolds. This convergence of biofabrication with nanotechnology is a largely unexplored but a growing focus for actually constructing directional, customizable biomaterial arrangements for promoting tissue regeneration, combined with the potential for also providing controlled bioactive delivery. So basically, this impetus for this nano progression in 3D printing lies with the fact that nanostructures, including nanoparticles, nanotubes, and nanofibers smaller than 500 nanometers, are basically poised to simulate native biological systems, thus allowing tissue regeneration via cell growth. Biopolymer matrix and nanostructure interactions result in these nanostructured materials having that enhanced functionality and mechanical properties which we are looking for. So this shows the procedure that we would follow at WADAP for designing a bioproduct scaffold using tissue engineering as an example. So firstly, we would select the appropriate biomaterials, which would be modified using various approaches such as cross-linking. Then we would select an appropriate approach for fabricating the 3D design, which could be electrospinning, phase separation, a sol gel approach, SLS, or 3D printing. After that, we then would consider the incorporation of various relevant bioactives, which are often nano-sized, allowing us to nanostructure the scaffold and further mimic the extracellular matrix. Then you would do the in vivo testing, of course, in an animal model as a preclinical model, such as a rat, in which a defect is created. For 3D bioplotting, the flow of events is shown here for creating various devices. And first, and almost most importantly, is the actual conceptualization and design of the optimal bioink for bioprinting. A computer-aided design is created with input into the design software, followed by bioprinting with alteration of various parameters in a layer-by-layer fashion. Okay, so now I'm going to discuss a few of our tissue engineering technologies developed here in WADAP, highlighting the use of 3D bioplotting and other techniques such as electrospinning, as well as nano enhancements to the scaffolds created. So here we have a 3D bioplotted hydrogel scaffold loaded with sodium indomethacin for the treatment of inflammation. The addition of anti-inflammatory agents to 3D bioplotted structural support scaffolds allows for the acute treatment of site-specific inflammation, as well as providing long-term structural support so that you can allow the tissue repair and rehabilitation to take place. The non-steroidal drug was incorporated into the architecture of the polycaprolactone scaffold via a nanostructured semi-interpenetrating network composed of your polyvinyl alcohol and polyacrylic acid. And your nano enhancement here was your nanostructured semi-interpenetrating network, which allows for the production of a dense hydrogel with strong mechanical properties and more efficient drug loading. So very importantly is that it's providing treatment where the inflammation is prevalent. So once again, providing that patient-centric approach. Here we see some of the characterizations of the scaffold, such as the microscopic images, highlighting the uniform adhesion of the scaffold within the octagonal structure when we do this uniaxial strain testing, as well as tracking of the hydrated scaffold, showing the biomimetic physico-mechanical properties, which basically we do on a state-of-the-art piece of equipment called a biotester. You can also see the inflammation responsive swelling of the scaffold with the subsequent site-specific release of your anti-inflammatory agent. Looking at a very important device here, a bio-inspired 3D bioplotted system for treating burn wounds, which of course we know here in South Africa alone is a very big problem, having not just physical implications, but also social and economic effects on the person and families affected. So according to the World Health Organization, there are about 1 million people worldwide having cases of burns that require medical intervention. So what we have proposed is this 3D printed scaffold having potential wound healing application. Formed by ring opening polymerization, we created a library of these new hydrogels for wound healing applications, showing low toxicity and fibroblast cell adhesion. A composite bioink was then created for 3D printing, having superior 3D printability and biofunctionality. The physical properties of the bioink was further controlled using various different 3D printing patterns. This shows the chemical interactive process involved in the design of the actual bioink. So initially here we see the cylindrical scaffolds that were printed, prepared as non-porous and porous scaffolds, and their physical properties were well controlled by their 3D printed architectures. Specifically, the porous 3D printed scaffold consisted of micropores because of the inherent material properties and macropores from the crosshatch printing pattern. The non-porous scaffolds only consisted of micropores. So these macropores increase the total porosity and surface area. Images of the wound areas were used to track the wound closure based on the initial wound area. And you can see there's wound contraction in the non-porous and porous group, which was significantly greater than compared to the gyelinate and Bactigras group. Scar formation was notably less in the porous group compared to all other groups. So here we have a 3D bioplotted implantable drug delivery scaffold, and this has application in bone tissue engineering. Traditionally, treatments for orthopedic defects included orthopedic implants, allografts, and autografts, and with these came challenges of infection, inadequate healing, inadequate donors, as well as morbidity at the donor site. So what was proposed here is a 3D bioplotted pseudobone drug delivery system inserted at the site of the bone fracture, and here we used a clavicle model. The implantable system was a copolymeric biomatrix that was based on a thermoresponsive gel and loaded with a statin drug as a regenerative factor. The nano enhancement here was functionalization with cells and growth factors. Here we just see an overview of the construction and the nano and micro architecture as well of the bone scaffold. Ex vivo evaluation was conducted using microscopic visualization and ultrasound using a vivo microimager and X-ray analysis as well. Osteoinduction could be visualized as cell attachment with subsequent proliferation. Evaluation on a fracture-induced human clavicle bone showed cell proliferation and fracture filling, as well as subsequent bone repair. Here we see another important approach for a wound dressing based on an alginate chitosan bioplatform. There's obviously the need to improve the performance of wound dressings to enable accelerated wound healing. And in order to improve the bioplatform, various approaches such as partial cross-linking, freeze-drying, and pulverization were also used. Here, the nano enhancement came in the form of chitosan alginate nano to microparticles to create a nano, micro, macro structure, which is required for enhanced tissue engineering. Also, the use of an adhesion motive for the development of a self-assembled scaffold. Bioplatforms had optimal fluid absorption, porosity, degradation, and mechanical properties, while also enabling drug delivery, cytocompatibility, and enhanced wound healing performance. So the first approach employed for improving the biomaterial properties and performance was a three-stepped approach, which involved the partial cross-linking, freeze-drying, and pulverization. And as you can see in the table, this cross-linking was confirmed by acid-base titration, following the actual surface charge or zeta potential, as can be seen in the table. Secondly, use was made of the RGD adhesion motive to aid the self-assembly of the scaffold, and the morphological changes were followed by ACM. As discussed, we could see the properties that were improved, as well as the various performance categories of the hydrogel platform, and we can note the complete tissue regeneration that was promoted with scarless skin tissue formation in a rat wound model. Here we see another approach that was employed for 3D bioplotting of bone scaffolds. We were looking here for a single-step fabrication approach to create a nanostructured scaffold, and this was engineered in a single step in situ with conjugation of a nanostructured polymeric scaffold. And there was also the inclusion of various nano additions. So the polymeric scaffold was engineered in situ employing sodium alginate, which was interacted with polyethylene imine to form a polyelectrolyte complex, and this was our very important bioink. Nano enhancement was via structuring with silica, nanoclay, or hydroxyapatite in the bioink. This was very important as inorganic structural support, so creating that mechanical strength, as well as the enhancement of osteoinduction. The anionic and cationic hydrogel were prepared with the inclusion of appropriate nanostructures for promoting bone tissue formation, and then subsequently bioplotted on our 3D bioplotter, enabling that simultaneous polyelectrolyte formation, creating the scaffold structure. Okay, so if we have visualization of the architecture, you can see this very intense scaffold roughness, which modulates the actual biological response through enabling and enhancing that cellular adhesion to the scaffold to promote tissue growth. We also visualized the important hydration of the scaffold via MRI, and then we did biotester analysis for determining the biorelevant physico-mechanical performance, because we have to see how the scaffold actually is going to respond in vivo when exposed to the pressures that are exerted on bones. In terms of the success of the scaffold in promoting bone tissue repair, successful seeding was observed. For the scaffold in the presence of osteoblast-like cells, we can see that after day 1, the cells demonstrated adherence and growth to the printed scaffold, and from day 3, the cells were forming colonies, which increased in density going towards day 7. Here we took a bit of a different approach, looking at post-modification chemically of 3D plotted scaffolds. This was to basically fine-tune the physical mechanical properties of those scaffolds. Surface chemical interactions and then functionalization of the scaffolds was undertaken by various approaches such as hydrolysis, aminolysis, and grafting as well. The nano enhancement was incorporation of nano strengthening agents to enhance the physical mechanics. Now we're going to take a turn to some very important approaches which we have employed for enabling neuroregeneration. As you know, the regeneration capabilities of the nervous system of humans is insufficient. There's incomplete repair and ability to regain function, and yet there has been no successful therapeutic scaffold for regeneration of damaged nerves. In this instance, we looked at developing a 3D printed self-assembled biomaterial artificial extracellular matrix for nerve regeneration. Obviously here the important key features were the composition of that polymer bioink, which was a semi-synthetic hydrogel, providing those adhesion motif groups for enhancing cellular adhesion, also being thermoresponsive and UV cross-linkable. The peptide was conjugated to the hydrogel for successful incorporation of native peptides while maintaining the original polymer behavior and creating a 3D printable system. So now we are looking at scaffolds that were developed specifically for spinal cord injury, and this formed the doctoral and ongoing cutting-edge work of my colleagues Prof. Pradeep Kumar, as well as the doctoral work of Dr. Purnima Rambarun. Due to the complexity of the spinal cord, of course, you cannot have spontaneous regeneration, repair, or healing. Paralysis is permanent and incapacitating. You guys yourselves know during motor vehicle accidents, as one example, the severe spinal cord injuries that can result. Innovative paradigm shifting strategies are needed to advance the treatment of spinal cord injury. So the strategy employed here is to bridge the lesion site with a nanobiotract within a scaffold. Nano enhancement that can be considered is biomimicking your Bergman tracts as an implantable neuroscaffold, providing the foundation for neuroregeneration in spinal cord injury. We want to activate stem cells to facilitate in vivo neural regeneration. So here we can see the electrospinning setup that was used for actually fabricating nanofibrous scaffolds for the spinal cord injury repair. We did image analysis of those scaffolds as well as microscopy. The alternate approach developed by Prof. Kumar focused on an innovative cryogelation technique to create a neurosponge that had the required strength, elasticity, and resilience as seen from the photographs, as well as a nano and microarchitecture mimicking that of the spinal cord, as we can see in the SEM images. So for preclinical evaluation, a traumatic spinal cord injury model was created in the Sprague-Dawley rat. Of course, this is a category 6 surgery. You are transecting through the cortical neurons, interneurons, sensory neurons, motor neurons, and your central canal. Both the nanospine scaffold as well as the neurosponge were evaluated, and they were inserted to bridge that gap within your spinal cord. Of course, there are ethical considerations that come into all of these surgeries, preclinical assessments, and we will discuss this a little further as we go along. So here we can see the functional recovery occurring in the Sprague-Dawley rat model observed over 4 weeks for your nanofiber scaffold. And here we can see the recovery that's observed for your spinometric cryosponge scaffold after 4 weeks. You can see complete joining again of the spinal cord that has occurred. This is just video visualization of that functional recovery occurring over the 4 weeks. You can see that the rat has basically returned to almost full functionality after 4 weeks. So ethical considerations, I mean, of course, this is a traumatic surgery. The spinal cord injury model is category 6 as mentioned, so it is debilitating. However, the results speak for themselves and bring us closer every time to a pertinent solution to tissue regeneration for spinal cord injury in humans. Another important aspect of neuroregeneration is specifically looking at traumatic brain injury, which is a severe challenge for 21st century medicine. What we proposed is the design of a novel neuromimetic 3D scaffold system, which is nano-reinforced and hydrophiled in a cryogel. This basically has bioresponsive capabilities in terms of being a shape memory system, which is soft, permeable, and has a robust deformable network. This is based on Dr. Mohamani's PhD research and was followed by in vivo analysis as well in a Sprague-Dawley rat traumatic brain injury model. So nanofibers were prepared using the electrospinning technique, and these had diameters between about 120 to 600 nanometers, which is a similar range that's noted for the native extracellular matrix. The cryogels were prepared using a cryogelation approach, giving an interconnected macropore structure with a predefined architecture. And then the hydrogel was prepared by chemical cross-linking to enhance the stability of your whole structure, which is otherwise water-soluble. So basically, this 3-in-1 scaffold was prepared stepwise, where the nanofibers were then embedded in your cryogel matrix, giving a nano-reinforced cryogel scaffold. And this was then filled with a protein-based hydrogel. And you can see how the structure is biomimicking the brain tissue scaffold structure. So here from the digital photographs and histology, we can see that the scaffold for the cavity lesion shown is a temporary platform at the cavity site. The brain tissue encompassed the scaffold rather than shrinking away from it. And this tissue scaffold contact is so essential to support potential tissue integration by allowing cells in the surrounding areas to migrate into the scaffold. There was architected internal vascular connectivity within the scaffold, stemming from its porous design and allowing the blood to perfuse into the scaffold. And the scaffold remained for at least 28 days, and this time is important to accommodate the slow process of repair, tissue reorganization, and extracellular matrix replacement by cells. Pertinent behavioral testing was also done, such as the cylinder test, tactile sensitivity, and neurological severity scoring. Now I'm going to give a brief glimpse into one aspect of our pipeline in tissue engineering, which is my focus, and these are some nano-embedded 3D bioplatforms for ocular tissue regeneration. So if we look at the leading causes of blindness in individuals over 50, it's cataract, glaucoma, age-related macular degeneration, and diabetic retinopathy, which is all due to degeneration in the retinal area. The use of nanoparticles as delivery vectors for gene therapy in the treatment of retinal diseases has been under investigation, but there are still barriers limiting their clinical efficacy. Recent developments have suggested the use of a combined approach, a combinatorial approach. So you have targeted gene delivery using nanocomplexes, and these are then embedded in your bioscaffolds. So we're basically focusing on the design of a gene-eye system using a copolymer nanocomplex capable of compacting the genetic material that we've selected for tissue regeneration and conjugating this to a 3D bioplatform, which will also be pertinent for driving retinal tissue regeneration. What we see here is the various routes by which we can actually administer ocular nanosystems to enhance the tissue engineering approach. I started looking at the implantation route, but there are various other routes, and also enhancing the permeation of these nanosystems through ocular barriers. This is why it's also important to consider the nanosystem structure for this permeation as well as for enhancing ocular tissue interaction. Here we can see an interaction, for example, of a positively charged nanoparticle with the ocular surface as well as the subconjunctival space of the eye. So what we're looking at here is that actual mechanism of operation of a nanosystem that's released from a bioplatform for ocular applications such as tissue engineering. Here we looked at the inflamed eye model created in the New Zealand albino rabbit. We obtained confocal images showing the actual affinity of the nanosystem for the inflamed cells. Also, what we note is a Trojan horse mechanism for internalization of the actual entrapped drug into your ocular cells. And in this animation, we see the release of a composite nanosystem from an implant based on the inflammatory stimulus. So we see the targeted delivery of your nanosystem to the retinal tissues in the inflamed eye with a subsequent bioresponsive erosion of the bioplatform in which it was embedded. And then you have your subsequent reduction in inflammation. So once again, we see the actual patient-centered application of this delivery system because it's responding directly to the level of inflammation. Could this be a potential ocular vaccine delivery system? We have initiated a project as well in this regard. Because despite your positive recent developments in vaccines, for example, the COVID vaccine, you also need a more efficient vaccine delivery system that overcomes disadvantages of current platforms. So the advantage of an ocular delivery system would be that it doesn't actually require special training for administration. The ocular mucosal immunization route has advantages over the parenteral route. And certain populations, think of children and individuals with bleeding disorders, would also be advantaged through the ocular delivery route. In this slide, we can just see some of the preclinical analysis that was conducted for nano-enabled bioplatform for ocular applications, showing the implantation procedure and histological analysis undertaken to note the reduction in inflammation in the rabbit's eye. What I'll just briefly wrap up with is some of our established WADAP technologies that are further being applied for 21st century problems. I mentioned the 3 C's: cancer, communicable diseases, and COVID-19. One of the aspects is the oral delivery of therapeutic proteins and peptides. The challenge with this is the low bioavailability orally, the enzymatic degradation that occurs, instability, the need to deliver multiple bioactives at once, and co-formulation of antibodies due to genetic variability. One of our solutions was a CoreMelt oral tablet, which was gastrointestinally protective, provided stimulus responsive spatial temporal release, and can be designed as an antibody ligand. Importantly, it's non-invasive oral route, simplified for patient compliance, 3D printable, extends the therapeutic window as well. The group has done a lot of research on anti-MUC16 antibody Prince. This arose because of challenges arising from poor drug penetration through mucus, and also this between chronic HIV and cancer, specifically like ovarian cancer. Our solution was a MUC16 antibody structure mimicking 25. Essentially, we incorporated this within a nanomicelle, which specifically targeted mucin antigens on cancer cells, and the anti-mucin antibodies can be internalized by the tumor cells, enabling the drug-loaded nanomicelles to gain entry, delivering the chemotherapeutic within the tumor cell. The potential of this for application in vaccine delivery must also be considered. The benefits of the system are the effective targeting of anti-HIV or cancer bioactives, reduced infection and cancer spread, protective immunity, and exploiting deregulated expression in TB pericarditis. Some of the technologies that also further application for 21st century medicine include dermal microneedles for application in wound healing and skin cancer, which was patented, and this could have important applications for the delivery of a buccal vaccine or antigens. Also, systems like drug-eluting devices, which we have developed for intravaginal delivery, for example, and intraocular delivery. These can have applications in the delivery of various microbicides as well. Chronotherapeutic applications of our oral delivery systems, solid lipid nanoparticle delivery of genetic material, cell therapeutics. We also have a spherocyte technology, and this is what I developed during my master's research as a delivery system orally administered for the treatment of TB. This could have applications in other communicable disease treatments, gastroretentive systems also for treatment of various communicable diseases and infectious diseases, intestinal patches, applications of these systems in animal health, for example, in the treatment of enterotoxigenic E. coli. So a number of these therapeutic approaches which I discussed are encompassed within our 6 patent families, specifically the resorbable wound dressings and biodegradable implants. In terms of tissue engineering, the largest challenge is really balancing all the performance objectives for successful scaffold integration within areas of biological and physical complexity. So a large volume of the research shows there's a great advancement in one direction, which is biocompatibility, but the mechanical strength needs to also be considered. And you can see in a lot of the technologies that I discussed, this is an important focus of ours. Also the integration of appropriate porosity into scaffolds for enhanced cell viability and promoting the growth of vasculature throughout the repaired tissue. We need that biomimicry approach. Also, future research into novel nanostructured bioinks and scaffolds for gene delivery for enhanced tissue regeneration, as I discussed as an example for ocular tissue regeneration. There is the further advancement of the 3D bioprinting to progression into organ printing. Experts project that in less than 20 years, we're not far away from actually producing a fully functioning heart. And of course, this is still challenged by the intricate nature of the vasculature of the heart. What we must also consider are the ethical considerations of this, printing full organs, for example. I mean, are we playing God, or is it a necessary step in the right direction? So that brings me to the end of my talk. Thank you all so much for listening on the other end. Thank you so much to my colleagues within WADAP for the inspiring research, Prof. Chinara, Prof. Kumar, Prof. Marimutu, and Prof. Kandia. Thank you a lot to Previn for organizing this talk once again, and to Dr. Soon Shiong for sharing his lecture platform with me. Take care.
Thank you, Prof. Lisa. We loved listening to your super informative presentation. I really think what you do is so amazing, but we do have some questions for you before you go. So let me know when I can begin.
Sure, go ahead. Thanks.
So 3D bioprinting brings several ethical considerations. Going forward, how do we as healthcare professionals ensure equal access to these breakthrough treatments?
That's a very good question, and I think a very important consideration in South Africa. I mean, it is a technology that you want to be made widely available. The thing is, obviously, with 3D printing progressing as it is becoming, as I mentioned, a cheaper approach actually. And what I feel is that 3D printing facilities can be distributed widely, not only within manufacturing institutions, but also within clinical settings as well. This will enable that personalization approach, which we're talking about. Also, the use of biomaterials that are readily available within South Africa and that can be readily transported to those facilities for actual printing. I do not think that it's an approach that is going to exclude the masses. I actually think that it's one that will embrace the masses rather.
Thanks, Prof. Lisa. That sounds really amazing for the future of medicine. Another question is, there is hesitance surrounding the clinical safety of 3D bioprinting. How do we overcome this and ensure safety so that we give people these life-saving treatment?
Thanks so much for that question. Dr. Soon Xiong also brought it up in terms of SAHPRA, and the regulation of medical devices is something that is very important and has come into play specifically since around 2020. So, of course, this is very similar as you would see with the FDA regulation or the European Union regulation of medical devices. So safety has to be assured in terms of that before it can be approved for distribution to the population.
Thanks, Prof. Lisa. And there are ethical questions surrounding the use of bioprinting for human enhancement. For example, bioprinting may be used to manufacture enhanced bones and replace regular human bones that are stronger and more flexible, increase muscle performance by making muscle more resilient and less likely to become fatigued, or lung capacity could be improved by replacing it with an artificial lung that can increase oxygen efficiency in the blood. In this way, human enhancement would have a dangerous but incredible impact on society. Bioprinting could create a culture without disease or infection. What is your take on this?
Well, I mean, at this stage, the need for these medical devices that are bioprinted is if you have a medical need. The only way that you would have authorized access to these devices is if you have a condition or a fracture or where you need a replacement of a certain tissue or an organ. Of course, as we know, even with medicines, these find pathways to be abused, for example, the uses of steroids as well. But basically, what we're really looking at is the development of devices to repair damage in the human being, not to enhance functionality.
Thanks, Prof. Lisa. That sounds really promising. And what are your thoughts concerning the notion that selling organs on the black market is deemed a problem, but the production and selling of bioprinted organs seems to fall outside this law?
Well, I wouldn't say it falls outside this law because it has to be regulated. The distribution of medical devices has to be regulated within South Africa, as I mentioned, under SAHPRA. So where this would occur, it would also be a black market. It's not the authorized distribution. So it would have to also be controlled, especially as the use of 3D printed devices becomes more widespread.
So these are all considerations that the regulatory authority has to take into account as well, because the unauthorized and unethical use of any devices could lead to serious harm if it's in the wrong hands, of course.
Thanks so much, Prof. Lisa, for answering all these questions. I'm sure all of us learned so much, especially with the ethical side of it and what you do. I'm now going to hand over to my colleague Previn, who will do the vote of thanks.
Thank you so much.
Previn, I think you're muted.
Thank you, Timera, and thank you, Sinan, for giving me the opportunity to speak. So I think everyone can agree that today's lecture from both speakers was extremely innovative, it was revolutionary, and we can all agree that we've learned so much. And we are so grateful to Professor du Toit as well as Dr. Soon Cheong for offering such an informative lecture, giving up time of their schedule, of their very busy schedule, to lecture us as medical students and as health science students across the faculty, for which we'll ever be so grateful too. And I think what we can learn from today's lecture, very importantly, as sentient and intelligent beings, our science and technology had taken humankind to greater heights. However, we must remember that our social constructs, attitude, and perceptions regarding the social ills of society, such as sexism, misogyny, and homophobia, need to correspondingly also take the front seat as much as science and technology does. Because while science and technology take humankind to the next level, we must also remember that our ethics and morals are what keep us there, and man without ethics is a wild beast loose upon society. So again, I would like to thank our speakers, Professor du Toit, as well as Dr. Soon Cheong, for taking time out of their very busy schedule to lecture us, to inform us about the current advances in technology, and I think we can all say with great certainty that the future is really here. I also want to thank Professor Kevin Behrens, our HOD at the Steve Biko Center for Bioethics, for his continued support in the Bioethics Society and his advice and provision of skills and equipment that allow us to have these events and to spread the knowledge across to the student body. I also want to thank everyone from SAMHSA as well as the Students Bioethics Society for making this event a success, and most importantly to all our guests for attending this event. And please contact us via our social media or email addresses if you have any questions going forward. Thank you once again, and I hope that you all have a wonderful evening. Thanks, everyone.